The question I have is, could you explain why we need to transform stresses? So let's start answering this question by reviewing how we represent the state of stress at a certain point, both in the three-dimensional and two-dimensional cases. Here I have the three-dimensional state of stresses marked on a three-dimensional differential element with respect to the x, y, z Cartesian coordinate system, whereas here I have a two-dimensional state of stresses marked on the xy plane on a two-dimensional differential element. For the purpose of the discussion here, it is sufficient to consider the two-dimensional state of stresses. So this is what we will consider in answering this question. Next, let's address the question of what is meant by the transformation of stresses. Supposing, say, we have a two-dimensional element subjected to the stresses shown in this picture. To be precise, I should be calling these components of the stress at this point. But these components are defined with respect to this xy coordinate system. Now let's say I consider the plane AB inside this differential element oriented like shown in this picture. Now the question is, what about the stresses on this plane? Are they related to these components? To avoid cluttering this picture, it's pretty common to draw the plane outside this differential element like shown in this picture. The plane AB is drawn parallel to this plane, the plane that we are interested in looking at the picture stresses on, and the stresses on this plane are sigma prime in the normal direction and tau prime in the shear direction. If this angle is theta, then you can easily verify that this angle is theta. In practical terms, transforming the stresses mean basically finding stresses on an inclined plane like this. It can be shown that sigma prime is a function of sigma x, sigma y, tau xy, and theta. And similarly, tau prime is a function, but it's a different function of sigma x, sigma y, tau xy, and theta. And these functional relations are what are called the transformation rules. Now let's try to address the question of why is there a need to transform stresses. There are usually many reasons. Let's go over a couple of them here, starting with checking the failure of bonds. Say we have a rectangular one-dimensional member like shown in this picture subjected to an axial force of 10 kilonewton. Supposing, say, this one-dimensional member was formed by bonding two separate pieces, using a glue along this inclined plane. Say we want to make sure that when this axial force is applied to this one-dimensional member, the bond doesn't break. Since the strength of materials are defined in the form of stresses, first we need to know the stresses acting on this inclined plane. So here's a 3D view, here's a 2D view. We need to know the magnitudes and the directions of the sigma prime and tau prime. Defining this angle as theta and placing a two-dimensional Cartesian coordinate system like this, the problem that we have boils down to this. Alright, so here I am showing the state of stresses on this two-dimensional differential element defined with respect to the xy coordinate system. And we have the tensile stress of 100 kilopascal acting in the x direction. There is no stress in the y direction, and there is no shear stress, right? And we need to find the stresses on this plane right there, whose normal is inclined at theta to the positive x direction. Now you can see checking the failure of the bond on this inclined plane boils down to the stress transformation problem. Another related reason is checking the failure of a homogeneous material using a specific failure criterion. In this particular example, I will consider the Tresca failure criterion. The Tresca failure criterion says that the maximum shear stress in the material should be less than or equal to K, where K is the shear strength of the material, for the material to be safe. So this problem boils down to finding the maximum shear stress in the material, right? So what exactly does it entail? So let me go back and take our early example for the discussion here. This is the state of stress, and the stresses sigma prime and tau prime are the stresses on this plane AB, whose normal is inclined at theta to the positive x-axis. We know as theta changes, the magnitude and the direction of sigma prime and tau prime are going to change, right? And this is exactly what happens. As I keep increasing theta from 0, when theta becomes equal to 62 degrees, this happens. The shear stress on this plane becomes 0, and the normal stress becomes the maximum possible for this point. And in this example, sigma max is going to be 38 kilopascal. To keep this picture clean, I'll leave the units out, but it's implied that all of these numbers are stresses in kilopascal. Alright, if I keep rotating by another 45 degrees, this happens. The shear stress on this plane assumes its maximum possible value, and in this example, it's going to be 18 kilopascal. There is normal stress, but the shear stress is going to be the maximum possible. And if I keep rotating by another 45 degrees, this happens. The normal stress becomes the minimum possible, and the shear stress becomes equal to 0. And you keep rotating it by another 45 degrees. The shear stress assumes the maximum value one more time. And the normal stress on this plane becomes exactly equal to the normal stress we had over here, which is 20 kilopascal. But the direction of the shear stress on this plane is opposite to the direction of the shear stress on this plane. In other words, here we have the clockwise direction. Here, this is going to be counterclockwise direction. The maximum and the minimum normal stresses are called the principal stresses. And of course, the maximum shear stress at this point is plus or minus 18 kilopascal. But even for the 2D case, there is the third direction, right? The direction perpendicular to the plane. The shear stress in the third direction are 0, but the normal stress, sigma 3, may or may not be 0. Now considering all three directions, the maximum shear stress at this point depends on the magnitudes of these three stresses, sigma 1, sigma 2, and sigma 3. Let's say sigma min here is the minimum of the three principal stresses, and sigma max is the maximum of the three principal stresses, right? And then of course, the third one would be the intermediate principal stress. You can show that the maximum shear stress at this point then is sigma max minus sigma min divided by 2. Then applying the failure criterion, the Tresca failure criterion, tau max should be less than or equal to K for the material to be safe. Here K is the shear strength of the material. We'll talk about all these details in another video, but the bottom line here is that we need to find the maximum and the minimum principal stresses at that point, meaning we need to perform stress transformation. So these are two examples why we need to do transformation of stresses, but there are others, and hopefully we'll run into some of them in the future.